The May 2019 historic tornado outbreak in the United States in the second half of May. Severe strong tornadoes in Tornado Alley. Many tornadoes outside of Tornado Alley, especially going towards the East Coast. Why so many tornadoes in 2 weeks? These graphs are from the National Weather Service, National Oceanic Atmospheric Administration, NOAA, specifically the Storm Prediction Center out of Norman, Oklahoma, which is where the National Weather Service is headquartered. And on these graphs we have red for tornado reports, blue for straight line wind damage reports, and green for hail. You can see mid-May, the 15th and the 16th, not too much happening, just one tornado between those 2 days. 17th is our first outbreak with very neatly lined up tornadoes going from northwestern Kansas into central Nebraska and the Oklahoma Panhandle into central Kansas. Pretty much perfectly straight lines going from the southwest to the northeast, with a few tornadoes also in Texas. Not too many straight line wind reports today. You can see most of that energy that's coming, the total energy of the system, was being transferred to tornadoes more so than wind reports. More tornado reports on this day than wind reports, with 95 hail reports for a total report of 186 severe weather events. So going to the 18th, it becomes much more of a wind event than a tornado event. 35 tornadoes with 267 wind reports and 45 hail for a whopping total of 347. On the 19th, we see our first little outbreak in the northeast. More straight line wind events than tornadoes, but still some tornadoes. And you can see that we see a sort of a multi-day pattern forming as well, which is, these systems moving across the U.S. through the jet stream. Besides that random tornado in Arizona on the 20th, pretty much everything was once again in a diagonal line going from the southwest to the northeast, from the southern part of the Texas Panhandle up into Missouri, not far from Joplin, where that F5 was 8 years ago. And an even amount, roughly 90 of wind and hail. Here on the 21st, we see some stuff in the Central Plains. And as we go into the 22nd, we see this storm system getting moved through the jet stream further east, going up into the Ohio Valley, also southwest and northeast orientation. 23rd, we sort of see this dipole of a new system starting to form in the south central plains of Tornado Alley and the remnants of the previous system in the northeast. The Tornado Alley storm from the 23rd becomes better formed. On the 24th, we see that southwest to northeast orientation happening again, but this time with a little more of a northward orientation. By the 25th, we see that system move into the northeast and more development start up. Really part of the same system on the 25th. The 26th, we see our first outbreak that is directly east of the Front Range of the Rockies with 37 tornadoes. And just one quick thing here on the 26th. I believe out of the entire outbreak of the second half of May, this was the highest number of total reports, 419. And I believe 527 was the highest number of tornado reports for the entire system, with 84 tornadoes on May 27th. And you can also see we've lost our southwest and northeast orientation. We are more going straight east-west. 28th, that continues, but becoming more spread out, going all the way from Colorado to New Jersey. The 29th, we see most of the tornadoes in Iowa, but many straight line wind events, particularly in the northeast, which happened to be a day that I went chasing. Didn't get to see any tornadoes that day in Pennsylvania, but got to see some pretty well-developed storms. And by the 30th and the 31st, we are through this crazy tornadic wind, rain, hail event. Looking at some of the mesoscale discussions out of the National Weather Service, you can see this is coming from my neck of the woods, but I think a lot of the dynamics are similar to the tornado-producing storms in Tornado Alley, with obviously more energy, more vorticity, steeper lapse rates, higher CAPE, all the ingredients. There's just more of them. Yeah, there's some different dynamics, of course. But I didn't save those mesoscale discussions because I was too focused on what was happening here in the Northeast. But we can see quasi-linear convective systems oriented southwest to northeast, which we've been talking about, as you can see in the discussion on the second half below. With discrete supercells, which is so important for these storms to really pull in energy from the areas around them, which aren't supercells. Bulk shear of 40 to 50 knots and CAPE levels around 1,500 to 2,000 joules per kilogram, which is quite significantly less than the 3,500 or so joules per kilogram, maybe even 4,000 plus that was happening in the Tornado Alley section of these outbreaks, but still significant for this area of the country. And let's move on here. I believe this was from the 28th or the 29th, but you can see not something we're used to seeing here in the Philadelphia, New York area, which is in Harrisburg, which is my neck of the woods. But you can see 4 tornado warnings simultaneously, and I think I had another one that I didn't upload, which was 6 or 7. And you can see here at the top right, that is New York City with the tornado warning near Newark and Elizabeth. And just some other mesoscale discussions here. You can see it's a lot of the same dynamics through the whole system. Convection is intensifying overnight because we're seeing these storms day after day. So in some ways, the next day's storm is feeding off the energy from the previous day's storm, as well as a jet stream that's locked in place, bringing in fresh amounts of heat and moisture. And we can see the shear environment was consistent through all these storms. What did differ is whether they were part of those quasi-linear convective systems or mesoscale convective systems, whether they're part of a bow echo system on a squall line or just part of an MCS. So some of those dynamics did differ across the country in terms of how these tornadoes formed, but the ingredients were relatively similar throughout. And this is a mesoscale discussion, and please ignore my cat making noise below the computer. But this is a mesoscale discussion from Texas and Missouri. And this was, I think, on a weaker day. But we had those steep mid-level lapse rates, which you really needed, which is in some ways tied into the shear. You need the lapse rate and you need the shear working on those steep lapse rates with a low-level 900 millibar, 950 millibar high moisture level getting pulled up into that cooler, drier air along with the rotation. So that low-level flow shear, and if you have the capping inversion, it's good. It's good for supercell formation. Going back to what I was saying earlier, this is coming from the Storm Prediction Center and their outlooks. You can see the yellow band. It's all part of the same system, coming from Texas all the way up into the New Jersey, New York border, with 2 dipoles, one in Oklahoma, one Pennsylvania, New Jersey. And you can see the shape of that warning box and how it kind of goes southwest to northeast, as we saw with so many of those tornadic storms. And then it kind of becomes more linear and east to west oriented as we head towards the east coast. We can see this is I believe the 500 millibar jet stream, and just how well that warning area lines up with the orientation of the 500 millibar jet stream. And I think this is the only 500 millibar jet stream I have in this video here, but I have a lot of other screenshots from throughout this 2-week period, and we saw that jet stream pattern get locked into place there for a significant amount of time without moving. This can be seen also on the surface map, which is we saw more stationary fronts. As the jet stream became locked in place, we saw these stationary fronts move with systems not getting flushed out as they typically would. You can see two stationary fronts here, one in Kansas, one in the Great Lakes, becoming one single stationary front going from Iowa to Pennsylvania on May 29th. With stationary fronts and a locked jet stream patterns comes flood risk as well. This is from the 29th, and we are looking at tornado watches in yellow, severe thunderstorm warnings in orange, flash flood warnings in red, flood warnings in light green, and flood watches in dark green. Very colorful map for the Philadelphia area, not something we typically see. As I mentioned earlier, I went chasing on 2 of the days and got pretty close to an F2, but not within camera distance. But still got to see this nice shelf cloud. And this is looking towards the north from southern Lancaster County, Pennsylvania, into Berks County, Pennsylvania, which is looking towards Morgantown right around the time that F2 hit, EF2. And another tornadically warned storm just to the west of Philadelphia. And just a little side note here, which is chasing in the Philadelphia area in the northeast, is you have terrain and rush hour traffic to worry about, both of which impeded my ability to get close enough to a tornadic supercell. This is the Harrisburg, Carlisle area going down to Chambersburg on 81. So you can see I try to stick to the valleys and not go into the terrain areas quite as much. So the big question that many people have been asking me, and is going around on social media, which is, what's going on with all these tornadoes? Why so many in such a short period of time? And why so many outside of Tornado Alley? One of the big things they have found is that tornado intensity hasn't actually changed that much with the changing climate, but there are items that are changing, which is that we are seeing these tornadoes happen in more intense outbursts and in areas outside of Tornado Alley. As we can see, this is from Michael Mann, very well-known climate scientist who first came up with the Hockey curve graph, which shows the relationship between CO2 and temperature, and also that there's this eastward shift out of Tornado Alley. Tornadoes have always needed the same ingredients to make those destructive vortices that we've become so used to. You need that warm, moist air near the ground and cold air, dry air above, and winds generally getting stronger with height and turning as you go. And the central U.S. has always been a good place for that, with the Rocky Mountains close by and the Gulf of Mexico to the south. And of course, we do expect warm, moist air to increase at low levels with climate change, but the changes in winds with height, wind shear, is projected to decrease on average with climate change. So we see less days with tornadoes, but when we do see tornadoes, those days have more tornadoes. And the other part of this is the jet stream. And the jet stream has been slowing down with climate change and forming more blocking patterns, which might explain why we see all these tornadoes day after day, whereas last year was a historically low amount of tornadoes, especially for the month of April in the U.S., which I believe was the first time in April that Oklahoma did not see a tornado in Oklahoma in the month of April in 2018. So that might be what we're seeing with climate changes. Lots of tornadoes all at once and then real quiet. On a real basic level, this comes back from the transfer of potential energy to kinetic energy, and specifically the transfer of potential energy in regards to height being transferred to kinetic energy in terms of motion. A ball that is held higher off the ground is going to have more potential energy than a ball that is held lower to the ground. These ideas were first explored by Dr. Jennifer Francis and Michael Mann, among others. And this idea stems from that the Arctic is warming 2 to 3 times faster than the rest of the globe. So although global warming is happening everywhere, the Arctic is warming much more quickly. And here's a graph, right? So warm air expands, to keep it simple for now. Cold air contracts, so cold air over the Arctic contracts, whereas warm air has higher height over the equator. But if the poles are warming more quickly than the equator, that height differential is going to decrease as the poles lift, so to speak. The pole heights lift more towards equatorial heights, and now there's less of a downhill slope. And along with the curvature of the Earth, these two items fundamentally create the jet stream. The height/temperature differential between the equator and the poles and the turning of the Earth. And I guess that is the end of my PowerPoint. I thought I had maybe 1 or 2 more slides. But this is just to demonstrate how climate change could be affecting tornado outbreaks, how it ties into the jet stream and blocking patterns, how shear is being affected, how moisture level and convection is being affected, and if this truly was just an anomaly year of having so many tornadoes in such a short period of time, especially going towards the mid-Atlantic and Northeast, or if this is something that we'll see in the future. But typically we have seen ridiculously resilient ridges, as they've been called, forming in California. We've been seeing more high pressure systems forming over the west as droughts intensify there. Is that going to help lock 850 millibar jet streams in that southwest to northeast orientation that we saw with so many of these tornado lines? Or is this May 2019 just a fluke year? The verdict is still out, but there's definitely some speculation. So thank you for watching, and I hope you got something out of it.